Welcome to all of my students. Today I will deliver lecture number 24. So first I will like to recall the result which I have discussed in the previous lecture. The result is that this is a D class, and if E and F two idempotents are D-related to each other, correct? And E, F and idempotents, they are D-related to each other. For example, E is here, F is here, isn't it? So there is element A in S, and there exists an inverse of A dash here, such that A dash is equal to E and A dash A is equal to F. Correct? So, so if E and F are D-related to each other, then they are the cross. E and F are D-related to each other, then there exists A dash such that A dash is equal to E and A dash A is equal to F. We will use this result basically in our upcoming results. One thing is that. And also we will use theorem 2.34 second part, which says that this is proposition 2.3.5 and this is theorem 2.3.4. If A be an element of regular D class, we have regular D class, correct? Class is regular. It means that every element is regular. So here it is A, it means that it is LA, this is RA. Now, if B is in D such that RA intersection LB contains idempotent, B is here, B is here. LA intersection, this is LB intersection RA. This is what RA intersection LB H class, and this is what LA intersection RB. This is H class. Intersection of L class and R class is what? H class, correct? So LA intersection RB, this is RA intersection LB. So if B is in D such that R intersection LB and LA intersection RB contains idempotent, this contains idempotent E, this contains idempotent F, correct? Then HB, this is of course HB, LB intersection RB. This is what? LB. This is RB. This is RB, and this is of course LB. So LB intersection RB, HB contains an inverse A star A. You say A dash such that A dash is equal to E and A dash A is equal to F. This is theorem 2.3.4 second part. And also no H class contains more than one inverse of A, isn't it? So in this way we can locate the inverses of the different elements, isn't it? Because no H class contain more than one inverse. Every H class will contain only one inverse, isn't it? So in this way we are able to, this theorem basically allows us to locate the inverse of a regular element. Element should be regular, correct? This is regular D class, regular. So these results are important and we will use these results in our upcoming results, correct? So basically what happens, idempotents are in the diagonal position. An element, inverse of element also occurs in diagonal position such that A dash is equal to E, A dash A is equal to F. These things we have. And E and F are related to each other, correct, of course. So now we move to proposition 2.3.6. Proposition 2.3.6. If H and K are together, if H and K are two group H classes in the same regular D class, then H and K are isomorphic. Then H and K are isomorphic. So first thing is to understand the problem, try to understand the problem. H and K are two group H classes, and if these H classes are group, it means if they are group, they contain an identity, and that identity will be the only idempotent, correct? So we can just say H is what? We say H is E, correct? That H is equal to E, and K is equal to what? We say HF, where E and F are what? Idempotents, where E and F are idempotents. Of semigroup F, correct? So H and K are the two group H classes in the same D class. They should be in the same D class, correct? It means that what? It means that E and F are D related to each other because they are in the same D class. For example, if you this is basically called egg box picture. This is HE and this is HF, correct? E is here and F is here. So here it is E, here it is F, correct? E and F are the idempotents. Now we take, what is our claim? Claim is what? Claim is HE is isomorphic to HF. We have to prove this, isn't it? So if we have to prove two groups isomorphic, what we do? We take a mapping, we define a mapping from HE to HF, and we try to prove that that mapping is homomorphism 1-1 onto mapping, isn't it? If it is so, then group will be isomorphic, correct? So basically, let A belongs to RE intersection LF. See, this is E element is here, so this is RE, correct? This is RF, this is LF. This is RE, this is RF, this is LE. Is it clear? So you take any element in RE intersection LF. So you take element RE intersection LF. It means that A should be where? A should be here. We take any element. Of course, there should be an element. So let A belongs to RE intersection LF. E and F are, of course, they are related to each other, of course, isn't it? So then by theorem 2.3.4 second part, there exists unique inverse A dash of A in LE intersection RF. As we know that, as we have seen in the theorem 2.3.4 second part, that if E and F are at the diagonally they are present, isn't it? then inverse exists diagonal position. Here it is a dash will exist here, isn't it? Such that a dash is equal to e and a dash a is equal to f. So here diagonal position is a dash, isn't it? So there exists unique inverse a dash of a in LE intersection RF. Of course, this is what LE intersection RF. This is what RE intersection LF, correct? Diagonal position such that a dash is equal to e, a dash a is equal to f. These things we have, correct? So, and also EA is equal to AF is equal to A, and A dash E is equal to FA dash is equal to A dash. Also this thing we have. Why? Because we know that EA is equal to A. We know that E is left identity for E acts as left identity. Why? Because E is in E. We know that the E is in LE, correct? So we know that the idempotent in L class act as a right identity. E is in RE. So idempotent E acts as left identity for RE. So you take E into A, isn't it? A is a member of RE. So when you operate E into A, then this E will act as a left identity. Correct. So E into A will be A. Correct. Now you see, as F, A is a member of LF also, and F is what? F being idempotent is a right identity. So A into F will be what? Again A, isn't it? We use basically the lemma in which we have proved that. Just I'm reading out. Every idempotent in a semigroup is a left identity for RE, and a right idempotent is every idempotent E in a semigroup is a left identity for RE and a right idempotent for LE, isn't it? Or you can say LF, doesn't matter. So in this way, similarly, A dash into E will be A dash, and FA dash into A dash is FA into A dash is equal to A dash. So these things are also true. Now we have to be careful by using Green's lemma. We will use Green's lemma now. Now you see how we use Green's lemma. See what we have. We have EA is equal to A. So by Green's lemma 2.2.1. Basically, if all of you remember that what is Green's lemma, if AS is equal to B, isn't it? Try to understand. This is this A and this is S and this is B, for example. So by Green's lemma, what we have, rho S by HA maps HA to HB. The fact is that if all of you remember the fact which I wrote, that rho S by HA maps HA to HB, and this mapping is 1:1 onto mapping, correct? Now you see, replace all, because AS is equal to B, then rho S by HA is from HA to HB. Now in the place of A, here it is E, in the place of S it is A, in the place of B it is A, correct? So now it is what? Rho A by HE, here it is HE, and HE to HB, B is what? A. So this will be. So rho A by HE is a 1:1 onto mapping from HE to HA, correct? Now we have A dash A is equal to F. So by Green's lemma 2.2.2, that is the dual of Green's lemma. it will be lambda A dash by HA is a 1-1-on-2 mapping from HA to HF, 1-1-on-2 mapping. So in a similar fashion as we have done AS is equal to B, in a similar fashion we apply Green's lemma with this on this, isn't it? We will get lambda A dash by HA is from HA to HF 1-1-on-2 mapping. Now you see it is a mapping from HE to HA, and this is a mapping from HE to HF. So composition of mappings will be from HE to HF. So phi is equal to rho A by HE into lambda A by HA. This is a composition map. This map is from HE to HF, 1-1-on-2 map. Correct? This is a composition map. Basically, it is a composition map lambda A by H, lambda A by HA. Basically, this is a composition map lambda A by HA, composition rho A by HE. But as we are taking the elements on the left side of the map due to following this book, therefore map is written like this: rho A by HE into lambda A by HA, and we denote it by phi. So it is the map from HE to HF. So we are getting a 1-1-on-2 map from HE to HF. Now what is this to show? We have to show that this phi is homomorphism also. So first thing is that we define a map. That map should be well defined, and after defining map we prove it that it is homomorphism. Now see how we prove it. Define phi from HE to HF by x phi is equal to A dash XA, where x belongs to HE. So of course map is well defined, because if x is equal to y, then A dash XA is equal to A dash YA. So map is well defined, trivially well defined. So no need to verify for that. So now we have to show that this map is homomorphism. Okay. So for any x1 comma x2 belonging to HE, x1 phi into x2 phi is equal to what? A dash x1a into A dash x2a. What is A dash? A dash is what? A dash, we know that A dash is equal to E. So A dash x1 E x2a, and x1 E x2, see x1 x2 are the members of HE, and E is the identity for this group, correct? So x1 into E is what? X1. So A dash x1, you write just since A dash is equal to E. Since A dash is equal to E. So it is what? x1 x2 A, since E is identity for group HE, correct? Now this is what? This is x1 x2 phi. So we have proved phi is homomorphism. x1 phi into x2 phi is what? x1 x2 phi. It means that phi is what? Homomorphism. So in this way we have proved that HE is isomorphic to HF, because we get a map which is 1-1-on-2 as well as which is homomorphism, isn't it? So all of you can write by yourself the remaining thing, that phi is homomorphism, therefore phi is isomorphism, hence HE is isomorphic to HF. So in this way we have proved this result. Now we move to proposition 2.4.1. Before moving to 2.4.1, I just like to tell some basic things. Let's move on 2.4.1. Proposition 2.4.1, let A, B be elements of a regular semigroup S, correct? Then A comma B belongs to L if and only if there exists A dash belongs to VA and B dash belongs to VB, such that A dash A is equal to B dash B. Second part, AB belongs to R if and only if AB belongs to R if and only if there exists A dash belongs to VA and B dash belongs to VB, such that A dash is equal to BB dash. AB belongs to H if and only if